Hi, I'm Jackie and my role is a coordinator.
Hi, I'm Jessica and I worked with the sensor.
Hi, I'm Mikhail, and I worked on the Rover.
Hi, I'm Kyle, and my responsibility is the monitor.
And our project is called Rovi.
The
little rover that could.
The objective of our project is for Rovi to traverse the Thunderdome in search of tokens.
Rovi must be able to move in straight lines and turns accurately. He must also be able to detect the tokens when he goes over them.
The sensor is able to detect objects on the board and determine where they are in inches.
The coordinator takes information from the sensor and the rover to note where it is and where it needs to be, and also to command the rover where to go.
This is the board. The orange objects are the calibration points.
On the left of the screen now, you'll see the yellow token. In the center, the green obstacle. And on the right, you'll see Rovi. The front half of Rovi is pink, and the back half of Rovi is blue.
To be able to communicate, all of the devices are connected in a network to the router. This router controls the message flow throughout the system.
Upon initialization, the coordinator gets information from the sensor about the locations of the obstacles and the rover. So what happens is the coordinator gets this information and then it builds a set of what people call waypoints. I will call them ideal locations. And with these ideal locations, the coordinator builds the set in order to get the rover to traverse around the arena in order to pick up these tokens. So in this diagram, you can see that the ideal locations that I consider are the center of the grid points or the grid spaces in this arena. Next, we know that the coordinator has to account for inaccuracies coming from the sensor and the rover. So with the sensor, we know that the sensor may not always give out the most accurate location of the rover. So the coordinator has to account for this by dealing with a threshold so that it knows within a small range, the variance of the sensor data will not affect it. In terms of the rover, we know that the rover may not always go exactly where it is intended to go. For example, the rover may only go 5 inches when it was expected to go 6 inches. So with this diagram, you can see that what the coordinator does is it builds a set of commands to get the rover to both move and to reorient itself by turning in order to get to the ideal waypoint that it was supposed to go to. So in this example, you can see that it has to move forward and then reorient itself to go downward and go to that ideal location and then reorient itself later to go to where it was supposed to go next. Finally, we know that the coordinator has to account for obstacle aversion, and there are two types of this. There is the no-edge obstacles and the edge obstacles. What happens is the coordinator has to deal with when an obstacle is either not near an edge or when it is near an edge. So what happens is with a no edge, the coordinator has to go around the obstacle, but then it can continue vertically. Whereas with an obstacle with an edge, it has to go around the obstacle, but it can't go vertically, so it has to continue horizontally.
The most useful thing to note about the monitor is that it receives messages from all the components in the system. It does this so that it can monitor the accuracy of the system and how well everybody's doing their jobs. The debug function gives a graphical interface so that each one of the components of the system can send a message to the monitor letting it know what it's doing at that time. The NetStat feature is used to track the performance of the communication between the different components in our system. The messages themselves are numbered in sequence from each device on the system, and that allows the monitor to keep track and notice if for some reason someone has dropped a message or forgotten to send a message or frozen up completely. I have a small state machine in place which moves from an init, which grabs the first message number, and it moves to either a green, a yellow, or a red state, which appropriately describes the state of communication with each component on the system. There are counters in place so that if a communication goes to red, meaning the link is broken, and then comes back to being green again, the system doesn't stop completely. It restarts and can come back to green, but there's a mark noting that, yes, we missed 10 or 11 messages in there somewhere. The monitor is also useful because it graphically displays what's going on in real time on the board. The sensors send information about the location of tokens, obstacles, and lead rover. We hard code that into the monitor ahead of time so that I can compare the known location of those items to the given location from the sensors. This allows the monitor to determine how well the sensors are performing their function. Additionally, the rover tracking allows us to keep track of how the rover moves from beginning to end all the way throughout the board. We can look at the pattern, ensure that we've covered the entire board, but also determine how many times and to what degree the rover had to make an adjustment to bring itself back on track.
The sensor I decided to use is the Pixie camera. The advantage of using this camera over other cameras is that it does image processing on the camera already. And the way that it does that is it's able to detect objects based on their color. And it's best to use more brighter or neon colors over darker colors in order for the sensor to pick it up better. Another advantage of using the Pixie camera is that it can collect two different types of object colors. It can detect a solid color or a color code. And the color code, if you use a color code, that's two different colors, and that also contains an orientation, which is useful for the rover since we need to know orientation for the rover. The communication that I use to get the data from the Pixie camera is over UART, and the data that is transmitted from the Pixie camera is in this order. And so first there is a sync value, which is 55AA, and then the next value is either 55AA or 56AA, depending on if it's a solid color or a color code. And then comes the checksum signature, which is the value of which object you're looking at. So if I have a green object versus a yellow object, then I can store the green object in signature 1 and the yellow object in signature 2. And that will be the value that's in signature on the data field. And then comes the X coordinate, Y coordinate, width and height of the object. And that's all this information is in pixels based on where the Pixie sees it in its screen. Next, I added calibration points to the board, which are the orange objects. The way that I set it up is I use 16 total calibration points, and I read them in directly at the beginning of the whenever the program starts, and store it into an array and sort it based on the location here. So it basically stores it in the array from this corner to this corner and then goes to the next row and does that using actually a quick sort function. Next, I use an algorithm to determine which block an object is in. So if an obstacle is in this block, then it's in block 9. The reason why this is useful is because I use bilinear interpolation, and that uses a unit square. So this is what a unit square looks like. It's 0, 0, 1, 0, 0, 1, and 1, 1. And this is the bilinear interpolation equation. Pretty much, I use this equation and create two different equations to solve for x and y, which will be a factor between 0, 1, and 1 of the unit square. And that factor will be multiplied by the inches of like the x direction. I made it 13 inches for one single block. And so I would do the x factor times 13 inches to determine where in that block in inches it is located. But I also can determine which block it's located in, so that I know how many inches in the x direction and y direction there are before you get to the block. And then since using these known locations, I can just add that to the inches I find the obstacle is located inside of the unit square. And another thing that we determined that we needed to do was to correct for height adjustment, which are these equations. And if you look on the screen, there is a image of a triangle, which is basically the layout for the Pixie camera and looking at the object, whether it's the obstacle or the rover, because those are on different heights than the calibration points. And so the Pixie camera sees it on one level, but we needed to adjust for the height of the obstacle and the rover. But the tokens are fine because they're still on the same level as the calibration points. And so using these equations, we could determine more accurately in the x and y direction where the obstacles and the rover are located.
The rover has two components to it. One, being able to control the motors to achieve as straight line as possible, and two, being able to detect the tokens that are on the board. To control the motors, you have two outputs going, one to each motor. Now, to get a straight line, you have to have both motors going at the same speed. To get what speed the motors are actually going, use an encoder pins that produce a pulse every time it reaches a Hall sensor. Now, to adjust to that, to make sure both of them are going at the same speed, you have a PID controller. PID stands for Proportional, Integral, and Derivative. These are three components used to calculate the difference between what the motor is actually moving and what it should be moving. Now, every time the motor encoder pins are off from the value they should be, that produces an error. That error is the proportional component. Over time, that error accumulates, and the accumulation is the integral component. Now, the change in error is the derivative component, but that one, because of its volatile nature, is usually not used. But by combining the proportional integral and proportional integral components, you are able to determine the error and quickly adjust to it, as opposed to volatilely adjust back and forth. Now, ideally, you'll want to start a motor, it'll start up and again reach the speed you want very smoothly. But in reality, even with a PID controller, it's a little volatile until it stabilizes. That period can be adjusted and shortened by optimizing the integral and proportional values and weighing them accordingly. Now, for the token detection, I chose reed switches and magnets. Every time a magnetic field is near a reed switch, it closes a circuit and produces a current through it. Problem is, at the center of the reed switch, it does not detect a magnet. It only works near the edges. So to solve that, I put three of them together in a way that if the magnet's near the center, it's still detected by the two outer reed switches right here. But if it's still partway through the center, it's detected by the center one, creating an even field of detection throughout the entire bottom of the rover.